In this module, you will learn about sequences and series. Take a look at the collection of numbers shown on the screen. Can you make out the order or the rule in which the numbers are listed in each collection? In the first collection, all the natural numbers are listed in ascending order. In the second collection, all the multiples of 5 are listed in ascending order. The third is a collection of the first 5 even numbers. And in the last one, the collection of squares of first 5 natural numbers has been listed. In each collection, there is a specific rule or order in which the numbers are listed. When a collection of objects is listed in a sequential manner or a definite order such that every member has a definite position, that is, it comes either before or after every other member, it is called a sequence. A sequence can also be defined as a collection of numbers arranged in a definite order according to some definite rule. The members or numbers that are listed in the sequence are called its terms. The terms of a sequence are denoted by A1, A2, A3 and so on up to AN, where A1 denotes the first term, A2 the second term, A3 the third term, and AN denotes the nth term of the sequence. For this sequence, 5 is the first term, 10 is the second term, 15 is the third term, and 35 is the seventh term. Observe that the subscripts denote the position of the terms in a sequence. If we say the nth term of a sequence, it means that the term is at the nth position in the sequence. The nth term is denoted by A with subscript n. An is also known as the general term of the sequence. A sequence is finite or infinite, depending upon the number of terms in it. If the number of terms in a sequence is finite or countable, then it is called a finite sequence. And if the sequence goes on forever or has an uncountable number of terms, then it is called an infinite sequence. For example, the sequence of natural numbers and the sequence of all the multiples of 5 is an infinite sequence. However, the sequence of the first 5 even numbers and the squares of the first 5 natural numbers is a finite sequence. The terms of a sequence can be expressed by an algebraic formula. For example, consider the sequence 1 by 2, 1 by 4, 1 by 8, 1 by 16, and so on. The first term of this sequence, 1 by 2, can be written as 1 by 2 raised to the power of 1. The second term, 1 by 4, can be written as 1 by 2 raised to the power of 2. The third term, 1 by 8, can be written as 1 by 2 raised to the power of 3. The fourth term, 1 by 16, can be written as 1 by 2 raised to the power of 4. Similarly, we can write the succeeding terms. In this way, we can say that the nth term of this sequence can be expressed as 1 by 2 raised to the power of n, where n is a natural number. Using this nth term of the sequence, we will be able to find any term in it by substituting the term value in place of n. Thus, the 8th term of this sequence is given by 1 by 2 raised to the power of 8, which is equal to 1 by 256. In some cases, an arrangement of numbers in a sequence like 1, 1, 3, 7, 17, 41, and so on has no apparently visible pattern. But the terms of this sequence are generated by the relation given by A1 is equal to A2 is equal to 1. The third term can be obtained by adding the first term and 2 times the second term. The fourth term can be obtained by adding the second term and 2 times the third term. In this way, we can obtain the nth term of this sequence by adding the n-2th term and 2 times the n-1th term for n greater than 2. Likewise, we can describe the sequence 1, 1, 2, 3, 5, 8, and so on as shown. This sequence is known as the Fibonacci sequence. Sometimes, it is practically impossible to express the terms of a sequence by means of a particular algebraic formula. Such sequences can only be described verbally, like the sequence of prime numbers 2, 3, 5, 7, and so on. A sequence is a collection of all images of a function x from n or any subset of n to x, where n is the set of all natural numbers and x is any set, maybe of objects, events, or numbers. It implies that the domain of the function is the set of natural numbers. Hence, a sequence can be defined as a collection of all images of set n under x. The notational representation of 1 under x is denoted by x with subscript 1. Similarly, the image of 2 under x in notational form is written as x with subscript 2. And likewise, we denote the sequence as shown, where the subscripts denote the position of the terms in a sequence. Sequences are also called progressions because the terms in a sequence progress in a definite manner, obeying some specific algebraic rule. Let us now learn about series. Consider a sequence with the terms A1, A2, A3, A4, and so on. Then, the expression A1 plus A2 plus A3 plus A4 and so on up to AN is called the series corresponding to the given sequence. Mathematically, the expression obtained on adding the terms of a sequence is called a series. Here, A1 is called the first term, A2 the second term, and AN is called the nth term of the series. A series is finite if the given sequence is finite, and infinite if the given sequence is infinite. In summation notation, the infinite series A1 plus A2 plus A3 plus A4 and so on up to infinity can be abbreviated as sigma AN, where n is from 1 to infinity. Similarly, in summation notation, the finite series as A1 plus A2 plus A3 plus A4 and so on up to AN can be written as sigma AK, where k is from 1 to n. The summation representation of a series is also known as the compact form of the series. In this module, you will learn about arithmetic progression. As we have learned, a collection of numbers arranged in a definite order according to some definite rule or pattern is called a sequence. Each number in the sequence is called a term, and the term in the nth position is called the nth term. Now, take a look at the patterns in the sequences shown here. Is it possible to write the next term in these sequences? Yes, by following the rule or pattern, it can be done. In the first sequence, a term can be obtained by adding 5 to the term preceding it. That is, the nth term can be obtained by adding the n-1th term and 5, which is the difference between two consecutive terms. Similarly, in the second sequence, each term can be obtained by adding 10 to the term preceding it. That is, the nth term is equal to the n-1th term plus 10. In both the sequences, we see that successive terms are obtained by adding a fixed number to the terms just preceding it. Such sequences are called arithmetic progressions. Mathematically, a sequence is said to be in arithmetic progression if every term, except the first, is obtained by adding a fixed number to its preceding term. The fixed number is called the common difference and is obtained by subtracting any term from its succeeding term. That is, d is equal to the nth term minus the n-1th term. The general form of an arithmetic progression is of the form a, a plus d, a plus 2d, a plus 3d, a plus 4d, and so on, where a is the first term and d is the common difference. Here a plus d is the second term, a plus 2d is the third term, a plus 3d is the fourth term, and so on. Likewise, the nth term, which is also known as the general term, is denoted by a with the subscript n and is equal to a plus n-1 into d. With the help of this general term or nth term, we can find out any required term in the sequence without actually finding the preceding terms. The sum of the first n terms of an arithmetic progression is n by 2 into 2a plus n-1 into d, or n by 2 into a plus l, where l is the nth term or the last term of the arithmetic progression. Now, let us verify some properties of an arithmetic progression one by one. First is, if a constant is added to each term of an arithmetic progression, then the resulting sequence is also an arithmetic progression. Consider an arithmetic progression with the terms 2, 4, 6, 8, and so on. On adding 3 to each term of the given sequence, the resultant sequence is 5, 7, 9, 11, and so on. Observe that the resultant sequence is also an arithmetic progression with the first term 5 and the common difference 2. That is, the common difference of the resultant series is equal to the common difference of the original series. Similarly, if a constant is subtracted from each term of an AP, the resulting sequence is also an AP. Next, if each term of an arithmetic progression is multiplied by a constant, then the resulting sequence is also an arithmetic progression. For example, let 5, 8, 11, 14, and so on be an arithmetic progression. Its common difference is 3. if we multiply each term of this sequence by 2, then the resulting sequence 10, 16, 22, 28 and so on is also an arithmetic progression with the common difference 6. Observe that the common difference of the resultant sequence is also a multiple of the number with which the sequence is multiplied. Similarly, if each term of an arithmetic progression is divided by a non-zero constant, then the resulting sequence is also an arithmetic progression. If the corresponding terms of two arithmetic progressions are added, then the resulting sequence is also an arithmetic progression. Let us consider two arithmetic progressions, 2, 4, 6, 8 and so on, and 3, 5, 7, 9 and so on. On adding the corresponding terms of two arithmetic progressions, we get the sequence of terms 5, 9, 13, 17 and so on. This is also an arithmetic progression. Observe that the common difference of the resultant sequence is the sum of the common differences of the two given arithmetic progressions. Similarly, if the corresponding terms of two arithmetic progressions are subtracted, then the resulting sequence is also an arithmetic progression, provided that the common difference of the two given sequences is not the same. Let us now prove one more result. That is, if the nth term of any sequence is a linear expression in n, then the sequence is an arithmetic progression. Let the nth term of the sequence be equal to an plus b, where a and b are real constants and n is equal to 1, 2, 3 and so on. For n is equal to 1, we have the first term as a plus b. For n is equal to 2, we have the second term as 2a plus b. For n is equal to 3, the third term is 3a plus b. Similarly, n minus 1th term is equal to a into n minus 1 plus b. Now, let's find the difference between consecutive terms. T2 minus T1 is equal to a. T3 minus T2 is equal to a, and so on. Lastly, the nth term minus the n minus 1th term is also equal to a. Therefore, the common difference of the sequence T1, T2, T3 and so on up to Tn is a, which is a constant. Hence, a sequence whose nth term is a linear expression in n forms an AP. Let us now learn to form an arithmetic progression by inserting the desired number of terms between any two terms. Given two numbers a and b, we can find a number c midway between them such that the resulting sequence of the three numbers forms an arithmetic progression. That is, we can find a number c such that c minus a is equal to b minus c, or c is equal to a plus b upon 2. Such a number c is called the arithmetic mean of the numbers a and b. Mathematically, the arithmetic mean between two numbers is a number that, when placed between them, forms with them an arithmetic progression. It is denoted by capital AM. In general, we can insert any number of terms between two given terms such that the resulting sequence is an arithmetic progression. Let us insert n terms between a and b such that the resulting sequence forms an arithmetic progression. This resulting arithmetic progression has n plus 2 terms, where a is the first term and b is the n plus 2th term. Now, the n plus 2th term is b. This implies a plus of n plus 2 minus 1 into d is equal to b. It further implies that d is equal to b minus a upon n plus 1. Now the inserted terms can be obtained by adding d successively to the first term. Let us consider one example. Insert 4 numbers between 2 and 32 such that the resulting sequence is an arithmetic progression. Let A1, A2, A3 and A4 be the 4 numbers between 2 and 32 such that 2, A1, A2, A3, A4 and 32 form an arithmetic progression. There are 6 terms in this sequence. Using the formula for the nth term, the 6th term, 32, is equal to 2 plus of 6 minus 1 into d. On simplifying, we get d is equal to 6. Thus, A1 is equal to 2 plus d, which is equal to 8. A2 is equal to 2 plus 2d, which is equal to 14. A3 is equal to 2 plus 3d, which is equal to 20. A4 is equal to 2 plus 4d, which is equal to 26. Hence, the 4 numbers between 2 and 32 such that the resulting sequence forms an arithmetic progression are 8, 14, 20 and 26. In this module, you will learn how to calculate the sum of first n terms in an arithmetic progression. A mason is laying bricks for a narrow staircase. For every step, he needs to add 4 bricks to the previous step. The staircase requires 25 steps. If you were to order the bricks for the mason, how would you determine the total number of bricks required for the staircase? APs display an interesting property that can help us derive a generic formula for calculating the sum of n terms. Take an example of a sequence of numbers 2, 4, 6, 8, 10 and 12. If you add the first term 2 to the last term 12 in the sequence, the sum of the 2 terms equals 14. Similarly, if you add the second term to the 5th term and the third term to the 4th term, you get 4 plus 10 equals 14. 6 plus 8 equals 14. As you can see, the result of these additions is equal. This property can be observed in all APs, including reverse APs. For example, if you reverse the given AP, you get 12, 10, 8, 6, 4, 2. Now try adding the first and the last terms of this AP, that is 12 and 2. The sum is 14. Similarly, if you add the second term to the 5th term and the third term to the 4th term, the sum is 14. This shows a pattern that we can use to derive a formula for the sum of n terms. Let's consider a standard arithmetic sequence where a equals first term, d equals common difference, and n equals number of terms. The first term is a. The second term will be a plus d, and so on. In this way, you can compute each term till the nth term. Let the sum of these terms be s. Now, let's consider the reverse of this AP. In the reversed AP, the last term, a plus n minus 1 multiplied by d, appears in the first position, and the first term, a, in the last position. The sum of the terms of this AP also will be s. Now add the corresponding terms of both the APs, that is, first term to first term, second term to second term, and so on. While calculating, you will find that the sum of the corresponding terms are equal in every case. Thus, we get 2a plus n minus 1 multiplied by d in every case. As there are n terms, the total sum will be equal to n multiplied by 2a plus n minus 1 multiplied by d. As we are adding the two APs, the sum of n terms will be doubled, that is, it becomes 2s. So to get s, that is the sum of n terms of an AP, you have to divide the equation by 2. Thus, you get the formula for s. S equals n divided by 2 multiplied by 2a plus n minus 1 multiplied by d. This expression can be arranged as follows: a plus n minus 1 multiplied by d. This implies that s is equal to n divided by 2 multiplied by the first term plus last term. Remember the Mason's problem? Using the formula for the sum of n terms, you can now determine the number of bricks to be ordered for the staircase. You can see that the number of bricks in the staircase forms an AP. According to the given data, the first step will have 4 bricks. Therefore, the first term A equals 4. Common difference D is 4. The number of steps is 25. This is equal to the number of terms in the progression, that is n. You can apply the formula for sum of n terms to the given data. Substituting the values of n, a, and d in the formula, you get the value for the sum of n terms, s. After simplifying, you get s equals 1300. Therefore, the mason requires a total of 1300 bricks to construct a staircase of 25 steps. In this module, you will learn about geometric progressions. Observe the pattern in the sequences shown. Following the same pattern, let's try to write the subsequent terms in each case. Beginning with the first sequence. The first term of this sequence is 10. The second term is 20. The third is 40. The fourth, 80. The fifth, 160, and so on. The ratio of the second term and the first term is 2. Also, the ratio of the third term and the second term is 2. Likewise, if we find the ratio of each term to the term just preceding it, we find that it is 2. Hence, we can generalize that the ratio of the n plus 1th term to the nth term is equal to 2 for all n greater than or equal to 1. It implies that n plus 1th term can be obtained by multiplying the nth term with the constant 2. Therefore, the 6th term is 2 into the 5th term, which is equal to 320. The 7th term is 640. We can find the other terms in a similar fashion. Similarly, for the second sequence, the ratio of n plus 1th term to the nth term is equal to 1 by 2 for all n greater than or equal to 1. It implies that the n plus 1th term can be obtained by multiplying the nth term with the constant 1 by 2. Hence, the 6th term of this sequence is half of the 5th term, which is equal to 1 upon 64. The 7th term is half of the 6th term, which is equal to 1 upon 128. The subsequent terms can be found in a similar manner. Such sequences, where each term except the first one can be obtained by multiplying its preceding term by a non-zero constant, are called geometric progressions. Mathematically, a sequence is said to be a geometric progression if each term except the first one can be obtained by multiplying its preceding term by a non-zero constant. This constant is called the common ratio and is obtained by dividing any term except the first term by its preceding term. It is denoted by R. Let us now consider a GP with the first term A and the common ratio R. Then the second term of this GP is obtained by multiplying the common ratio R with the first term A. The third term is obtained by multiplying the common ratio R with the second term. The fourth term is obtained by multiplying the common ratio with the third term, and so on. In this way, the subsequent terms can be obtained. Likewise, the nth term can be obtained by multiplying the common ratio R with the n minus 1th term. The nth term is also known as the general term of the GP and is denoted by A with subscript n. With the help of the general term or the nth term, we can find any required term in the sequence without actually finding the preceding terms. Thus, we have the general form of GP as shown. Now notice that the terms of a GP follow some definite pattern as shown. The first term, A, can be written as A into R raised to the power of 1 minus 1. The second term, A into R, can be written as A into R raised to the power of 2 minus 1. The third term, A into R square, can be written as A into R raised to the power of 3 minus 1. The fourth term, A into R cube, can be written as A into R raised to the power of 4 minus 1. This pattern suggests that the nth term of the GP should be given by A into R raised to the power of n minus 1. Remember that the nth term is also called the general term of the GP. Here the common ratio, R, is defined as the ratio of any term, except the first, to its preceding term, and is expressed as n plus 1th term divided by the nth term for all n greater than or equal to 1. A finite GP has a finite number of terms, while an infinite GP has an infinite number of terms. Correspondingly, the sum of the finite number of the terms of a geometric progression is called a finite GP series, while the sum of the infinite number of terms of a geometric progression is called an infinite GP series. Consider a GP with n terms, having the first term as a and the common ratio r. The sum of these n terms of a finite GP is a finite GP series. Let's denote this GP series by Sn. While finding the value of Sn, two cases arise. The first case is when r is equal to 1. Consider a GP with n terms, having the first term as a and the common ratio r. The sum of these n terms of a finite GP is a finite GP series. Let's denote this GP series by Sn. While finding the value of Sn, two cases arise. The first case is when r is equal to 1. The sum of n terms of the series is equal to a, so on, up to n terms. This is equal to n into a. The second case is where r is not equal to 1. Multiplying both the sides of equation 1 by r, we get r into Sn is equal to a into r plus a into r square plus a into r cube plus so on, up to a into r raised to the power of n minus 1 plus a into r raised to the power of n. Denote this by equation 2. Now, subtracting equation 2 from equation 1, we get Sn minus r into Sn is equal to a minus a into r raised to the power of n. This further implies 1 minus r into Sn is equal to a into 1 minus r raised to the power of n, or Sn is equal to a into 1 minus r raised to the power of n divided by 1 minus r if r is less than 1, and a into r raised to the power of n minus 1 divided by r minus 1 if r is greater than 1. The general term Tn of a GP is equal to the sum of the first n terms minus the sum of the first n minus 1 terms of that GP. Let's now have a look at some simple tricks to find the terms of a GP when their sum is given. When we have to find an odd number of terms in a GP whose sum is given, then it is convenient to take the middle term as a and the common ratio as r. Thus, three terms are taken as a upon r, a, and a into r, while 5 terms are taken as a upon r square, a upon r, a into r, and a into r square. When we have to find an even number of terms in a GP whose sum is given, we take a upon r and a into r as the two middle terms and r square as the common ratio. Thus, 4 terms are taken as a upon r cube, a upon r, a into r, and a into r cube, while 6 terms are taken as a upon r raised to the power of 5, a upon r cube, a upon r, a into r, and a into r cube, and a into r raised to the power of 5. In this module, you will learn about geometric mean. Given two numbers a and b, a number m can be found between them, such that a, m, and b form a geometric progression. Such a number m is called the geometric mean between a and b. Mathematically, the geometric mean between two numbers is a number that, when placed between them, forms with them a geometric progression. Let's now derive the formula to calculate the geometric mean. Let m be the geometric mean between two numbers a and b. Then a, m, b are in GP. This implies the common ratio m upon a is equal to the ratio b upon m. This further implies m square is equal to a into b, or m is equal to square root of a into b. Hence, the geometric mean between two numbers a and b is the square root of a into b. Let a be equal to 4 and b be equal to 16. Then, the geometric mean m between them is given by the square root of 4 into 16. This is equal to square root of 64, which is equal to 8. Hence, we can say that 4, 8 and 16 form a geometric progression. In general, we can insert as many numbers as we like between any two given numbers. Let us find n numbers g1, g2, g3 and so on up to gn between any two given numbers a and b. On inserting these numbers, the resulting sequence a, g1, g2, g3, so on up to gn and b forms a GP having n plus 2 terms. Let a1, a2, a3 and so on up to a n plus 2 represent the first, second, third, and n plus 2th terms of this GP, respectively. Now n plus 2th term is b. This implies a into r raised to the power of n plus 2 minus 1 is equal to b, or a into r raised to the power of n plus 1 is equal to b, or r raised to the power of n plus 1 is equal to b upon a. This implies that the common ratio r is equal to b upon a whole raised to the power of 1 upon n plus 1. Now, let us find the numbers g1, g2, g3 and so on one by one. g1 is the second term, which is given by a into r. Substituting the value of r, we get a into b upon a whole raised to the power of 1 upon n plus 1. g2 is the third term, which is given by a into r square. Substituting the value of r, we get a into b upon a whole raised to the power of 2 upon n plus 1. Similarly, the fourth term of this GP is a into b upon a whole raised to the power of 3 upon n plus 1. Likewise, the subsequent terms can be obtained. The last inserted number, which is the n plus 1th term, is equal to a into b upon a whole raised to the power of n upon n plus 1. As we have already seen, the arithmetic mean between two numbers is their average. That is, the arithmetic mean between the two numbers is a number which, when placed between them, forms with them. As we have already seen, the arithmetic mean between two numbers is their average. That is, the arithmetic mean between the two numbers is a number which, when placed between them, forms with them an arithmetic progression. Let's now see the relationship between the arithmetic mean and the geometric mean. Let A and G be the arithmetic mean and geometric mean of two positive real numbers A and B respectively. Then A is equal to A plus B upon 2 and G is equal to square root of A into B. Now, let's calculate A minus G. This is equal to A plus B minus 2 times square root of A into B whole divided by 2. Now, A can be written as root A whole square and B can be written as root B whole square. This implies A minus G is equal to root A minus root B whole square upon 2, which is greater than or equal to 0. Therefore, A minus G is greater than or equal to 0. This implies A is greater than or equal to G. Thus, the arithmetic mean between two positive real numbers is always greater than or equal to their geometric mean. In this module, you will learn to find the sum of n terms of some special series. By now, you're familiar with arithmetic progression and geometric progression. The sum of n terms of an AP is equal to n by 2 into 2a plus of n minus 1 into d, or n by 2 into a plus l, where L is the nth term or the last term. It is denoted by S with subscript n. And for a GP having n terms, the sum of the series is equal to NA if R is equal to 1. A into 1 minus R raised to the power of n divided by 1 minus R if R is less than 1, and A into R raised to the power of n minus 1 divided by R minus 1 if R is greater than 1. We shall now find the sum of the first n terms of some special series. Let's first find the sum of the first n natural numbers. To note the sum of the first n natural numbers by Sn, let this be equation 1. On rearranging the terms in the sum beginning from the last term, we get the same series again. Denote this by equation 2. Adding both the sides of equation 1 and equation 2, we get 2 times Sn is equal to 1 plus n plus 2 plus n minus 1 plus 3 plus n minus 2 plus and so on up to n minus 1 plus 2 plus n plus 1. This implies 2 times Sn is equal to n plus 1 plus n plus 1 plus so on n times, or 2 times Sn is equal to n into n plus 1. This implies Sn is equal to n into n plus 1 whole divided by 2. Alternatively, the sum of the first n natural numbers can be found by using the formula for the sum of an AP. This series is an AP with the first term 1, last term n, and common difference 1. The sum of n terms is given by n into a plus l whole divided by 2. Or n into n plus 1 whole divided by 2. Hence, the sum of the first n natural numbers is n into n plus 1 whole divided by 2. The sum of the first n terms is denoted by summation of k. where k is from 1 to n. We now consider one example. Let's find the sum of the first 5 natural numbers. Let S5 denote the sum of the first 5 natural numbers. Then, by formula, we have S5 is equal to 5 into 5 plus 1 whole divided by 2. This is equal to 15. Let us now find the sum of the squares of the first n natural numbers. Let us denote the sum of the squares of the first n natural numbers by Sn. Now, we use the identity k cube minus k minus 1 whole cube is equal to 3k square minus 3k plus 1. Denote this by equation 1. Substituting k is equal to 1, 2, 3, and so on up to n. Successively in equation 1, we get 1 cube minus 0 cube is equal to 3 into 1 square minus 3 into 1 plus 1. 2 cube minus 1 cube is equal to 3 into 2 square minus 3 into 2 plus 1. 3 cube minus 2 cube is equal to 3 into 3 square minus 3 into 3 plus 1. We get the subsequent terms in a similar fashion. On substituting k is equal to n, we get n cube minus n minus 1 whole cube is equal to 3n square minus 3n plus 1. On adding the respective sides of all the above equations, we get n cube is equal to 3 into the sum of the squares of the first n natural numbers minus 3 into the sum of the first n natural numbers plus n. It implies that 3 into the sum of the squares of the first n natural numbers is equal to n cube plus 3 into the sum of the first n natural numbers minus n. Now, the sum of the squares of the first n natural numbers is Sn. Similarly, the sum of the first n natural numbers is equal to n into n plus 1 whole divided by 2. On simplifying, we get 3 into Sn is equal to 2n cube plus 3n square plus n whole divided by 2. Taking n common in the numerator and simplifying, we get Sn is equal to n into n plus 1 into 2n plus 1 whole divided by 6. Hence, the sum of the squares of the first n natural numbers is n into n plus 1 into 2n plus 1 whole divided by 6. The sum of the squares of the first n natural numbers is denoted by summation of k square, where k is from 1 to n. With the help of this formula, let's find the sum of the squares of the first 10 natural numbers. Let S10 denote the sum of the squares of the first 10 natural numbers. Then, by the formula, we have S10 is equal to 10 into 10 plus 1 into 2 into 10 plus 1 whole divided by 6. This is equal to 385. Let us now find the sum of the cubes of the first n natural numbers. Let us denote the sum of the cubes of the first n natural numbers by Sn. Now, we use the identity k plus 1 whole raised to the power of 4 minus k raised to the power of 4 is equal to 4k cube plus 6k square plus 4k plus 1. Denote this by equation 1. Putting k is equal to 1, 2, 3, and so on, up to n successively in equation 1, we get 2 raised to the power of 4 minus 1 raised to the power of 4 is equal to 4 into 1 cube plus 6 into 1 square plus 4 into 1 plus 1. Also, 3 raised to the power of 4 minus 2 raised to the power of 4 is equal to 4 into 2 cube plus 6 into 2 square plus 4 into 2 plus 1. And 4 raised to the power of 4 minus 3 raised to the power of 4 is equal to 4 into 3 cube plus 6 into 3 square plus 4 into 3 plus 1. The subsequent terms can be obtained in a similar manner. On substituting k is equal to n, we get n plus 1 whole raised to the power of 4 minus n raised to the power of 4 is equal to 4n cube plus 6n square plus 4n plus 1. On adding the respective sides of all the above equations, we get n plus 1 whole raised to the power of 4 minus 1 raised to the power of 4 is equal to 4 into the sum of the cubes of the first n natural numbers plus 6 into the sum of the squares of first n natural numbers plus 4 into the sum of the first n natural numbers plus n. Now, the sum of the cubes of the first n natural numbers is Sn, and the sum of the squares of the first n natural numbers can be written as summation of k square, k running from 1 to n. Similarly, the sum of the first n natural numbers can be written as summation of k, k running from 1 to n. It implies that 4 into Sn is equal to n plus 1 whole raised to the power of 4 minus 1 raised to the power of 4 minus 6 into summation of k square minus 4 into summation of k minus n. Now, let's substitute the values of the sum of the squares of the first n natural numbers and the sum of the first n natural numbers. On simplifying, we get 4Sn is equal to n raised to the power of 4 plus 2n cube plus n square, or 4Sn is equal to n square into n plus 1 whole square, or Sn is equal to n square into n plus 1 whole square whole divided by 4. This implies Sn is equal to n into n plus 1 divided by 2 whole square. Hence, the sum of the cubes of the first n natural numbers is equal to n into n plus 1 divided by 2 whole square. The sum of the cubes of the first n natural numbers is denoted by summation of k cube, where k is running from 1 to n. With the help of this formula, let's find the sum of the cubes of the first 7 natural numbers. Let S7 denote the sum of the cubes of the first 7 natural numbers. Then, by the formula we have S7 is equal to 7 into 7 plus 1 divided by 2 whole square. This is equal to 784.